What's up, everybody? Welcome back. Today, I want to implement two-factor authentication from scratch. And you might say, why? And I would say, I went out the other night. I was jogging down the sidewalk. Dumb mistake. Sidewalk, really bumpy. Comes out of nowhere. I eat some fucking concrete, some tasty concrete. And so does my phone. So the phone screen is shattered. I can't use it. I'm like, okay, fine. We buy a new one. We have, the resources to do so. I buy a Pixel 7. I let it die. Never charges. Doesn't turn on. So like once that thing goes to zero, I just can't use it anymore. Second phone in 2 weeks, freaking broken. And so I'm like, bro, I can't even like log into websites right now. And like, I don't think that I've done anything unreasonable. I tripped and I bought a phone and then it broke and I let it die, right? I haven't done anything unreasonable. And so like, I'm like, what even is like, what are all these codes on my phone? Why are they on my phone? What even are they? Do I need to be doing this? And so obviously in like classic Spheraphoria fashion, instead of like reading, we will just implement a TOTP client from scratch and we will see what the pieces are. And so I like looked this up a little bit earlier. We found Wikipedia article for TOTP. And in here, they link the standards document. RFC. What number is this? 6238. Is the webcam off for the same reason the phone is broken? Well, no, that's because my blinds are broken. Unrelated. I just tried to open them and then they like fell apart. And I'm like, okay, well, now they're stuck open. And I don't want you guys looking at my window. Because then you might be able to figure out where I live. Which would be bad. No looky-loos. So yeah, this RFC says, what is a TOTP? A TOTP is simply a truncate Hmac SHA-1. And I'm like, what the fuck is an Hmac SHA-1? So I type that into DuckDuckGo, and we pull up this Wikipedia page, Hmac. In here, I think I just searched, here they said, I saw Hmac SHA-1. So Hmac is like something that's built on top of SHA-1 or any hashing algorithm. We'll get to it. We'll get there. And in here, they're like, well, if you want to build something on top of SHA-1, you got to know SHA-1. So then we're like, RFC 3174, SHA-1. We'll implement this from scratch, work our way up to the top, okay? So like, what are the pieces of a TOTP? High level before we get into it. It looks like, TOTP is an HOTP with time. You throw some time in there. And I'm like, what the fuck is an HOTP? I don't know. HMAC based one-time password. Okay, so we're trying to do something that says, I want a one-time verification that I am me, right? And I believe what they're doing here, this is like probably incorrect in some way because I haven't really read this part yet. But like my understanding is that by doing this mathematical operation where you truncate, actually hold on, is it actually SHA-1 or is TOTP SHA-226? I don't know, we'll get there. But so by doing this operation, you are doing something called an HMAC, which is a hash-based message authentication code. So the idea here is you have some sort of box. We'll call it SHA for the purposes of this, but like, any sort of like cryptographic hashing function. The idea is you put like some stuff in and you get like fixed length out, right? So like maybe 256 bytes of stuff comes out. And the idea is it's really computationally easy to go this way, really computationally difficult to basically impossible to go this way. So it's like really hard for you to know what the input was for a given output. But if you both have that output, you're like, good, we agree, you are you. So I believe what they're doing in these hashed message authentication codes is they're saying like, in the context of what we're talking about, they're like, hey, here is your code. 1, 2, 3, 4, 5, 6. When you like scan the QR code on your phone for an authenticator app, it's giving you like a number. You like don't tell anyone that number. That number is super secret. You like somehow staple this number together with like time, right? And you get like you shove that through this box and you get something out. This is like skimming over some details because there are reasons why just hashing this isn't good enough, but like hand wavy, you're basically taking this information, trying to convert it into something that is like hard to reverse, and then you and the person who gave you the code both do it. You get the same numbers, and you're like, good to go. You're you. Pretty freaking sick. Yeah. So that is like kind of, I think the only thing that TOTP is it's like you're taking authentication code, hashed authentication code, using time as one of the inputs, and you're calling it a day. I think. I don't know. We'll see. We'll see. So let me just double check. The plan was to implement it from the bottom up, which I thought started with SHA-1, but I also thought it started with SHA-256 the other, like earlier when I was looking at this. So let me just double check that this really is SHA-1. TOTP algorithm. This variant of the HOTP algorithm. So basically we defined TOTP as HOTP KT, and then they defined HOTP as truncate an Hmac of SHA-1. So I think we're chill. I think SHA-1 is where we start. I think. And here he is. Here's the RFC. There is an implementation of SHA-1 in the Zig standard library, or maybe there was SHA-256, but I think like using that kind of defeats the purpose. You know, it's like not in the spirit of the stream, which is to do it all from scratch. So let's try to figure out what the fuck this thing is. They have overview of contents. We don't have to read that. Definitions of bit strings and integers. They're like, hey, sometimes we use 4-bit strings to implement to talk about a nibble. Okay. Here is, you know, you can have a bunch of 4-bit nibbles and they'll turn into like your typical hex encoding. They're like, we can use whole words. Great. And then blocks are 512 bits. And they may be represented as a sequence of 16 words. Okay. They're like, hey, we have some logical operations. You got your logical AND, your logical OR, your XOR, your NOT. You know, that's just like in Zig or C++, or like whatever. You got your like NOT, you got your XOR, you got your OR, you got your AND, right? We have all the pieces that we need to implement this. So we don't even really have to think about that part. They have X plus Y. Every time they're talking about addition, they're doing it with wrapping in 32-bit words. Cool. And they have a circular left shift, which is defined as S to the power of N, X, where X is a word, 32 bits, and N is an integer between 0 and 32, where they're shifting left and ORing in the shift of the right. So basically say like, we're rotating the bits, is basically what they're saying, right? So if you have like 101, if you were going to do like a left, what is this, like S to the 1 of 1001, this would be 0011, right? Because this 1 pops off the left and wraps around. Will you trust your TOTP enough to use it for GitHub? Well, I think that if we get it right, there's nothing to trust. I think like the math is the math, you know? I think there are other pieces of cryptography where it's not like that, but I think that like doing this is pretty straightforward. So maybe. It would be kind of like a good meme. All right, then they're talking about message padding. So they're like, hey, you are trying to use something, you were trying to like do it on some input. The message or data in the file should be considered as a bit string. Okay, the length of the message is the number of bits in the message. Okay, empty message has length 0. If the number of bits in the message is a multiple of 8, which everything that we ever do will be, yeah, just to kill these really secrets. Yeah, that part's hard. I think that part's actually difficult. But if we just store them in our head, what's more secure? Just memorize the codes. If we represent the number of bits in the message as a multiple of 8, for compactness, we can represent the message in hex. The purpose of message padding is to make the total length of a padded message a multiple of 512. SHA-1 sequentially processes blocks of 512 bits while computing the message digest. Okay, so we're saying SHA-1 needs to operate on chunks of 512 bits. So if you don't have enough, you need to throw some extra stuff on there. As a summary, a 1 followed by zeros followed by a 64-bit integer are appended to the end of the message to produce a padded message of 512 times n. The 64-bit integer is the length of the original message. Okay, sure. So it's not just zeros, it's like take the length of the original thing, shove it on the end, call it a day. The padded message is then processed by SHA-1 and n 512-bit blocks. Okay, so here are some padding rules. Suppose a message has a length of L, which is less than 2 to the power of 64. Before it is input to SHA-1, the message is padded on the right as follows. 1 is appended. For example, if the original message is this, you throw a 1 on the end. Great. So this is 0101, 4 zeros, 0101, 4 zeros, and a 1. Easy. Zeros are appended. The number of zeros will depend on the original length of the message. Right, because you need to put the length of the message in. So if the length of the message is a small number, then you pad more zeros maybe, or something like that? Maybe, we'll see. The number of zeros will depend on the original length. The length L of the original message. Example. Suppose the original message is the bit string this. After we put a 1, it is this. Since L is 40, right, this is a 40-bit string. The number of bits in the above is 41, and 407 zeros are pending, making the total 448. Oh, because you're basically padding with zeros until you have one 64-bit word to drop in, right, for the length. Obtain the 2-word representation of L, which is big endian, it looks like. And they're like, okay, well, the original thing was hex 28 or 40. Easy. Got it. Makes sense. Makes sense. We define a set of logical functions. Your topic switches faster than the Linux distro of a standard distro hopper. So true. What can I say? There's a lot of things wrong with the world that we have to look into, okay? It's not my fault that my phone ain't concrete, okay? It's not my fault that it doesn't turn on. These things just happen to me. The world is doing it to me, not the other way around. I'm a victim. Then obviously we have to do this, right? We can't not. Okay. A sequence of logical functions, F0 through F80 or F79, I guess, inclusive, is used in SHA-1. Each F of t, 0 to 79, or inclusive, operates on 3 32-bit words B, C, and D, and produces a 32-bit word as an output. So F at time step B, C, D is defined as follows for words B, C, and D. So for t 0 to 20, we do this. 0 to 19 we do this, 20 to 39 we do this, 40 to 59 we do this. Got it. Okay. A sequence of constant words is used in the SHA-1. Okay. Got it. So we have some initialization here that I'm sure that they'll explain to us. Okay, I think I understand. So we're going to implement these functions, these 4 functions. We're going to put these 4 constants somewhere. We're going to add some padding to an input. And here we go, computing the message digest. Here's the interesting part. This is the interesting part. Did you finish either your calorie or barcode things? No, there's no finishing here. We never finish anything. That's not the point. Finishing is for people with jobs. Okay. The methods given in 6.1.6.2 below yield the same message digest. This is a little loud. Can we just turn this down just a teeny bit? Thank you. All right. Although using method 2 saves 64 32-bit words of storage, it is likely to lengthen the execution time due to the increased complexity. I see. So there's 2 methods. And we'll just use method 1 because I don't really care. Because they're like, method 1 better. There are other computation methods which give identical results. Cool. Okay, so they compute the message padded as described in section 4. Sure, so section 4 was the padding shit. The computation is described using 2 buffers, each consisting of 5 32-bit words in a sequence of 80 32-bit words. The words of the first 5-word buffer are labeled as these. The words of the second 5-word are these guys that were those constants from above, I think. No. H is different. H is undefined so far. The words of the 80-word sequence are labeled W0 through 79. Got it. Okay, we will. Oh, here are the H's. Okay. To generate the message digest, 16-word blocks. Wait, what is 8? What is this 80-word sequence? Are these like the message that comes in? No, the message is the M's here. Oh, each block that we process, each 16-word block involves 80 steps, which are from these W's probably. Probably. I don't know. We'll see. Before processing any blocks, the H's are initialized as follows. Okay? Now, M1, M2 to Mn are processed. To process Mi, we proceed as follows. Divide Mi into 16 words, where W0 is the leftmost word. Okay. For T equals 16 to 79, let WT is this shit. Let A is these H values. Then we do this. Wait, where? So this has nothing to do with what are these functions that we were talking about earlier? Are just not used there, right? When they were talking about the... Where were those functions? These. Like, these are kind of inlined in the implementation there, right? These, I think. Let's double check. Okay, hold. B and C or not B and D. That's not in here at all. Oh, here's F. Never mind, F is down here. So these are those functions from above. So they go, for T is equals to 16 to 79, we use the previous invocations of T. Or of this W, right? Is this W that we're defining here? Oh no, sorry, W is not a function. W is just the word. Okay. Oh, I see. So you have 16 words here, 16 numbers. And here we're generating the next ones to fill out to 80, because we need 80 things. These are generated based off of the inputs. Then we have these constants. And we go for each, in our 80 steps, we look at the WT, which, you know, some of those are like directly from the inputs. Some of them are from like the things that we generated. We throw that in there. We use that function that was defined up here. We do a rotate of A, and then we use E, and we use K. Then we do all of this shit to like reshuffle our A, B, C, D, E. And then we move on here. Okay, wait, what is H0 used for here? Oh, A is used here. Oh, I see. So we have initial state of these H values. We put those into A, B, C, D, E. Then we use A, B, C, D, E to increment H values again. Okay. After processing this stuff, the output is the H's. All right, fuck it. Let's just fucking rip it. That seems doable. Right? Right? I think so. Main. Pub function main. Hi. Let's just fucking run it. Hi. Easy. Okay. So we're gonna have... Okay, so, like, SHA is processed in 512 byte blocks, right? But we are going to like feed, we're going to feed just like bytes one at a time, right? So kind of like the type of API I've seen for this before now is starting to make sense, right? Where is you have something where you go like pub function init, right? This will return our like SHA-1 structure, right? But then you also will have like push or update or something like that, where you will have, you know, our implementation and data, right? Now this thing probably needs to like process this data in 512 byte blocks, right? So we're gonna have some sort of like buffer. Sorry, 512 bit blocks, sorry. Right? And if this is not a multiple of 512 bits, there's also this guy, final, that people implement. And probably what this guy does is he like pads the buffer until 512 bits, then does the final block. You know what I mean? This is my understanding. Maybe not, but who knows? Okay. I think I saw, by the way, somewhere, I saw like test strings of like empty string. I guess we have Python for this as well. We can do like hash lib SHA-1 this. And we can kind of use this as our test, right? So like V is this, and I think it's like hex digest. Yeah. So here we can kind of use this as an example. I think also maybe we have SHA-1 sum. SHA-1 sum. Can we do like this? Is it like this? SHA-1 sum. So AD, is that like the same thing that we got from Python land? No, it's not. I think maybe they're doing like new lines or something. Doesn't final need to reserve the last 64 bits? I don't know what that means. Maybe. Anyways, we'll figure it out. Let's just start with a known 512 byte block and then figure out this interface after. I think that makes sense. So can we just make a 512 byte block that looks like test input. Well, I like the idea of a test input of empty string, right? Because then we can test like the padding logic as well. So let's do like a do SHA-1 block. Well, I guess we'll start here. So what is our like state for a single SHA-1? I think A, B, C, and D are A, B, C, D, E are temporary, right? I think that they are used for each block from H0, 1, 2, 3, 4, right? So let's do that. H is 5 U32s, right? So that's going to be H0, 1, 2, 3, 4. Yes. Okay. Let's just call it hash for now. We won't do this like final shit. And okay, part 1. Divide M. I guess we'll on init we need to set age, right? So here are our initial H values. Cool. Divide M1 into 16 words. So let's start right now by doing like a std debug. No, we won't. Oh, we need to pad. We need to pad first. That's the piece I'm missing. So var padded, I guess, is going to be a this size buffer. We can just put that on the stack. For now, let's just assume that the data is less than 1 block long. Okay. Then we can do like mem copy into padded. This. Like this. Okay, we copy that shit in. And then I think we need to like do padding. So how do we do that? Okay. 1 is appended. If hold on. This is only if it doesn't fit, right? The following specifies how this padding shall be formed. As a summary, a 1 followed by M0 followed by a 64-bit integer appended at the end of the message to produce a padded message of length 512 times n. So it doesn't sound like you skip this if how do I say this? Like if we are a multiple of 512, it doesn't seem like the logic changes. I don't think. And is this only on the last block? It has to be, right? Well, it's only at the very end. I would think so, right? Our appended to the end of the message to produce a padded message of length of 512 times n. The 64-bit integer the length of the original message. The padded message is then processed by SHA1 as in n 512-bit blocks. I see. So most of the time we're not doing this. Fuck. Let's just we'll just go this number is too high. But that's okay. We'll figure it. Yeah, I guess this is like the final step. Right? That we were talking about before. Right, so here we're like we'll figure it out later. I think we'll just do whatever makes sense here. And then if it breaks, it breaks. That sounds reasonable. That sounds reasonable. Okay. So I guess we'll do pad message. And we'll take padded. And then we'll say data.len was the original message length. Okay, that makes sense. So we're going like, it seems to me like you would just always put the 1 in there. And since we're working as on a byte stream, not a bit stream, we can write hex 80 immediately, right? I guess if we're really close to the end of the block, this won't work. But like, whatever. So var I is message len, probably. And then we go, while I is less than like block bytes is 512 array. Let's put this somewhere. So while I is less than block bytes minus 2, because we need no, minus 8, because we need 8 bytes at the end for the length of the message, we append zeros. Yes, but we forgot to put the I first. So buff I is 80, I plus equals 1. Okay. This makes sense so far. I think we should do a little assert here that I is less than block bytes minus 8, because otherwise this will break. This won't work. And then we just inject the length of the message, right? So we say buff I onwards. I guess stood debug assert that buff len minus I is equal to 8. I believe that makes sense. And then can we do a stood mem write int into this thing as a u64 of message len, I think. And we're doing big endian style. I think that makes sense. I think that makes sense. So can we do a little test here? So if we're saying pad message, so I guess we'll say like var pad buff is lock bytes u8. And we'll say mem copy pad buff 0 to 5 with hello. Okay. 1, 2, 3, 4, 5. Yep. And then we'll pad the message hello. And this is 5, right? Oopsies. So here we're expecting to see equal pad buff is the output, and we're expecting like hello plus 80 0 0 zeros to some amount. So what is block bytes? 512 over 8, right? 64. That makes sense. So we're looking for fuck. 64 minus 5 is 59. 59 minus 8 for the length is 51. So we're expecting 50 zeros. I think. I think. Sure. Okay. All 0 test paths. Great. What is it? It's like test, stood, testing, ref, all decals this or something. Yeah, okay. All 1 test pass. Does it fail? Like, does that mean is it right? No. God fucking damn it, dude. Why does this not get tested? Do I do this? There we go. Pad message does not fail. And here we go. Okay, so I took out a 0, right? I think it was supposed to be like this. Oh, expect equal slices. My bad. Okay, so like we expected this output, found this. Right, because we do also have to put in the value here. So can we do like pad buff, or not pad buff, 5. So I guess here we'll just do like this. 1, 2, 3, 4, 5, 6, 7, 8. Right, so we pad, then we get the length. We put an extra 0 by mistake. No? Oh, there we go. Okay, cool. So we're saying like message. We've got one bit followed by lots of zeros, and then message length. Easy peasy. That seems right. Earlier, CodeCat asked if Zig supports slice of U1. I think not in the way that you would think. Maybe if you do packed, maybe. But like, I don't think it's doing like the vector bool optimization, at least not by default. Okay, so we have padded our message, maybe. Okay, so then we take our message. So let's do hash block. Maybe like this. And I guess, do we hash in place? No, I guess we kind of are looking at self here. Because the output of the hash is only these h values, right? So we don't really care about everything here, I think. We'll see. We'll see. Okay, so first we get the first 16 words. I guess we're trying to get 80 of these U32s, right? So we start for 0 to 16. We take the words from the block, I think, right? So we're looking at like block. I guess it's like words I is equal to the block at like I times 4, 0 to 4. Like this, I think. Right, so every 4 bytes we pull in, I think. Not sure. Not sure. So what would we expect to see here? We would expect to see that the first word here is HELL, and the second word is O8000. I think. Because they kind of said that they're in the spec somewhere that everything's big endian. So everything is read left to right as most significant to least significant. So HELL would be like the 4 most significant bytes, I think. Okay. Then for 16 to 80, we are saying, can we show this word W? Just to make our like reference to spec easier. WI is equal to, can we call this like, I would like to keep using the letter, like the word S here for the function, but we need a way to like have a function called S that isn't like a problem. Maybe we could just do that here though. So S probably returns a U32. He takes in like amount, like the rotation and the value, right? Okay, so it's like we are doing a S1 using all of this stuff. So this is anytime we say T minus, that's I minus, or we'll just call it T. That makes our lives easier. And then anytime we see W bracket, we convert that to lowercase w bracket, find the other side, and then do this. Okay, and then our XORs are these. Okay. Looking good to me. Easy. Okay, then we say A is H0. Do we have to do like this? I guess so, fuck it. B, C, D, E. Okay. This is self dot now. Boom. Easy. Then, right, 0, 1, 2, 3, 4. It would be crazy if they just swapped the order in here just to fuck with us. You know, if they did 8, 0, 1, 3, 2, 4 or something, just to fuck our lives up a little bit. Okay. 4, 0 to 80, T. Because they're doing inclusive ranges. We are not. Temp is this. Okay. This is temp. These are all now variable because these are getting changed. And I guess let's find semicolons and hit enter. Okay. And then we'll lowercase all these. And then this is S30B now. Cool. Okay. We're getting close. We're getting close. Okay. This is S5A. Was it plus? We're doing wrapping addition for everything, they said. They said everything is 32-bit wrapping. Okay. I think that we will call this... maybe we will do function f here that takes in the, like, t value. B, C, D. That seems reasonable. Returns U32. And this is unreachable for now because we haven't implemented it yet. But that means that this can just be called FTB like this. This is lowercase. This is W with square braces. And this is K probably also with square braces. Now, we'll do K or T over 20. Okay, that makes our lives easier. So this is going to be 4 U32s, right? And he is going to be these guys. Right, because they are intervals of 20, right? 20, 20, 20, 20. Yeah, seems good to me. Delete till the equals, put a 0x, delete, end of word, change, comma, go, go, go. Easy. Yeah, sure. So now all that's left is implementing F and S, I think. All right. So those S was easy, I think. Here. So we'd say return val shoved left by rotation, or val shifted right by 32 minus rotation. Easy. Yeah. And then F was whatever they said. All right. Switch T. 0, 19. We do one thing. 20 to 39. We do this. 40 to 59. We do this. Switches are inclusive in this language, but for loops are not. Kind of fun. Kind of fun. All right, else unreachable. All right, and then we can start doing this. So this is B and C. I guess we should, just to reduce like copy paste errors, let's actually transform this, right, directly as is. All right, This is easy. Throw in some of these guys. Boom, boom, boom. Why is it dot 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 and switch and dot dot 4? Yeah, maybe you could do dot. Maybe you could do exclusive ranges in switches, but I haven't seen that, so I don't know. All right, so this is B and C, or B and D, or C and D. All right. Lowercase, and then the last one. This is the same, I think. B XOR C XOR D as the 20 to 39 case, but fuck it. The compiler can figure that out for us. And then let's do lowercase that and that. Perfect. Dude, what if this just kind of works? Can you imagine? Can you imagine if this just worked? So we are hashing. Oopsies, this is wrong. We are hashing the padded message, right? So we're going hash block padded. And here now this needs to be like, give me a little SHA-1, please. And so now, if we wanted to run this thing, we'd be like SHA-1 init. SHA dot hash. Let's hash an empty string for first. And then can we do, like, let's print out the hex representation of these H values at the end? Right, I think. I don't fucking know, man. Wouldn't it be crazy if this just worked? Wouldn't this be crazy if it just worked? I feel like I should have read the RC before stream. We read it just now, so you're not that far behind. Expected type 512U8. Yeah, that's wrong. So true. That 512 that we wrote was supposed to be a 512 over 8. Block size. Block bytes. Okay, expected type found U32 found U size at 96. Okay, I mean, yeah, we can just use a U size there. That's fine by me. That's fine by me. These rotation values need to be a U5. Okay, we'll do this. Okay. Error union is ignored. The hash can't fail, so I'm just used to throwing exclamation points all over the place, but we don't need them here. Okay, and then the question is does this look like what we did when we did Python 3? This. Import hashlib SHA-1 an empty string. No, not in the slightest. Okay. Not in the slightest, which means it's time to debug. Which means it is time to debug. So the first question that we might have is, oh, I mean, we're just getting the initial values of H0 to H4. We just forgot to update them at the end. We just didn't finish the implementation. So we did all of this stuff, but we did not do this last step. We did not do this last step. So let's try to format this a little bit. Okay, like this. That looks kind of right. Boom, boom, boom. And then these all get lowercase. Everything that says H0 here, this is like a macro that says, this is self dot H bracket and bracket. Perfect. Integer overflow. So all of these need to be wrapping. Holy fucking shit. That's right. That's the same fucking number, baby. Let's fucking go. Okay, so we can hash an empty string. That's fucking sick. That is fucking sick. And let's now, I guess we have to figure out how to hash like a variable length message, right? So first of all, can we try hashing ASDF? So we get this, and if we go, let's do a little like test pi, import hash lib, and we'll just do like hash lib SHA-1 sys argv1. Do you do like 2 bytes or something? How do you like string 2 bytes Python? There's a way. Encode. That makes sense. And then we print this, I think. Hashlib. Hashlib. Sys. And then we're like, okay, sick. So here we do ASDF, and then in our main, can we also just take this as an argument maybe? Sure. Args is this, we get the process name, and then we say 2 hash is args next. We crash if this is wrong, and then we write 2 hash here. And so then can we do SDF, and then this? Okay, bad news, those look different. Okay, but if we do empty string, they're the same, which means that our padding for an empty block is right, but everything else isn't. I think. Yeah, so why would that means that like the hash block thing is right, but the padding is probably wrong? Right? Like we know that this is generating the right output for an empty block, right? So that makes me think that the block that we're putting in is wrong. But the padding is also working. I don't know how to debug this. I haven't thought. Because like if things here are working. Okay, can we do something simpler? Run with A. Okay. If we are slicing the padded wrong, maybe std debug print This is the buffer length. And then can we print the content of, like, can we just print what we made? Does one of those strings contain n or is the encoding word? Yeah, good question, huh? You are right that we should double check that the Python is doing what we think. So can we say 2 hash is this? 2 hash mir. You know, that, like, Ramstein song? Maybe there's something wrong here. It's a byte string of A. Can we hard code hello for a second? Okay. Then can we hard code hello here? Yeah, I mean, they're not the same. But that was worth checking. Let's just do a little double check here. Okay. So can we print? Is this like a GDB angle? Maybe we like just kind of step through what we're trying to see. Is this going 1 byte too far? Let's just print the final thing at the end. What's going on here? Oh, forgot this. This looks weird, right? Why is there so much stuff at the... Oh, because we're doing hello, my bad. Right, so we have... How do I say this? This is man ASCII. H. H is 68. So we should be seeing 68, 65. We should be seeing 68, 65 for HE. Then the L is down here. So 6C, 6C, then an O, right? If we understand this correctly, 6F. 6, 8, 6, 5, 6C, 6C, 6F. Then an 8, then a bunch of zeros, then a length of 5. So I don't see any problem there. 1, 2, 3, 4, 5. Yeah, I don't see any problem. Let's go back to what they were talking about in the spec. SHA-1 is used to compute a message digest for a message or data file that is provided as input. The message or data file should be considered to be a bit string. The length of the message is the number of bits in the message. The empty message has length 0. Oh. The length is in the wrong fucking unit. Bits, not bytes. So this should be times 8 here. Times 8, and then, so this should be 40. Okay. They're both ignoring the input, but now these match, which is good. That's good. So can we just go back to doing sys arg v1 encode here? Cool. And then can we go to our main and go back to using our actual argument? So zig run A and Nice, baby. Let's fucking go. Ooh. Okay, we're gonna hope that our restriction on size here is fine. We're just gonna hope to fucking God. Because I don't want to do more. So, Hmac. This is the next piece of this thing. So we saw in the TOTP RFC, they're like, we want to do an Hmac SHA-1. So can we look for the definition of Hmac SHA-1? Maybe RFC, maybe? RFC 2104. Keyed hashing for message authentication. You know that SHA-1 is deprecated, right? Well, what do you mean by deprecated? Because, like, if I just look at the spec here, that's like, I'm just reading the spec of TOTP. It doesn't really matter if SHA-1 is not a, like, you know, oh, they may use these. Fuck! Fuck! I didn't realize that. Okay, well, how do they know? How do they know? Fuck! Okay, I was looking earlier at, like, authentication test. This. I think this is the site I was looking at. Auth test, maybe? This. So, how would this give me the information of which SHA is, or which hashing algorithm is being used? I tested this earlier by using HOTP. I just copied this secret in there. So let's see what their default is. Because I did... Oh, and in 6238, which is not the one we are looking at, by the way. Oh, no, it is. Okay, 6238. Can we look at, like, the source code for this thing? I just want to check if they're what hash algorithm they're using. If digest is none, they use SHA-1. Okay, so it's very likely that this is using SHA-1, but you can override it if you want. Sure. Okay, cool. Then we will keep going. Okay, so Hmac. What do they fucking do? Also, where is this one, right? Hmac. So they do a thing where they take the hash of a key, block size key derived by the secret key. They XOR it with a pad here. Then they concatenate it with another hash of the thing, XOR with this thing, and then a message, right? So what is the purpose of Hmac? The Hmac is supposed to say, hey, I have a secret, I have a message. How do I want to be fucking sure that you're the guy who sent those things, right? And so they're like, they talk about why you would do it this way down here in the Wikipedia article. So, like, you would think, kind of, that if you have some hashing function that can say, give me any input and give me, like, one-way output. Well, we've kind of seen by implementing SHA-256 that if you were to do, you know, take my message or take the key and the message, this is like a unique thing, right? However, because the hash is like iterative and done in blocks, then you can also like H key message and then like thing injected by someone else. This also generates like a hash that looks like you had the key, right? Because like the key came first and you're like, well, this whole chunk of stuff sure was hashed along with the key. I put my key and then the stuff. Oh, I get the same thing. So that's not good. So they're talking about like length extension attacks here. That's what they're talking But then they're like, okay, well, what if you have hash message then key? And it's like, well, if you ever find a collision of your message and a different message, then like you can replay, you can see, you can like, how do I say this? You have like two messages that yield the same result without ever knowing the key, which is also not good. So they're like, you know what? We'll just scramble it up a little bit more, basically. Is kind of like the hand wavy version of this, is to my understanding. They're like, we just scramble it up a little bit, we hash things twice, and we XOR in some like repeating numbers to like fuck with them a little bit, so that it's harder to like go backwards. And then they said somewhere in the Wikipedia page, they're like, yeah, and like we don't know of anybody breaking this shit. So do we have like that Python test that we had? Is there like hash lib? Can we like print hash lib? Like how do we print what's in here? I can't remember. Print functions in Python module. Dir. So do they have any like Hmac stuff in here? They have this. Do you have like hash lib SHA Hmac? Is that like a thing that we can do? Ah, it's like a different module. So you do like test Hmac pi. So if we want to do like import hash lib and mac or Hmac, then you can do this. And then like hex digest maybe. Hash lib, I did again. Perfect. Perfecto. Okay, so if we do everything right, then hopefully we can get the same outputs as the Python version. Where is this fucking Hmac RFC? Is it this one? Hmac, yep. Okay. So, definition of Hmac requires a cryptographic hash function, which we have now, which we denote by H, and a secret key, K. We assume H to be a cryptographic hash function where data is hashed by iterating basic compression function on blocks of data. We denote B by the byte length of such blocks. B equals 64 for all the above mentioned examples of hash functions. And by L, the byte length of the hash outputs. So L is 20 for SHA-1. So 5 times 4 is 20, so that is correct for us. And 64, surely 512 over 8 is 64. Yes. Okay. So we are in this case. The authentication key K can be of any length up to B, the block length of the hash function. Applications that use keys longer than B bytes will first hash the key using H, then use the resultant L byte string as the actual key to Hmac. In any case, the minimal recommended length for K is L bytes. Okay, cool. So do they talk about how they turn the key into a block? I guess we support any data that is shorter. So I think we're chill there. Okay, we define two fixed and different strings, iPad and OPAD, as follows. The byte 36 repeated B times, the byte 5C repeated B times. To compute Hmac over data text, we perform hash of K XOR XPAD, or OPAD. What are the two... This might be a stupid fucking question. Why are there two inputs to H? You know what I mean? Like, SHA-1 has one input, right? Which is the block. Right? So, what the fuck is this H function? Cryptographic hash function that we denote by H. Am I stupid? Isn't SHA-1 iterable? Oh, you think this is a concatenation? Oh, maybe. Because that's how they represent it here. They say, yeah. So in this Wikipedia page, they said the double block says concatenation. I see. So the comma here in this RFC is just like stick them together. Okay. So we are hashing K XOR iPad. Okay, so what is our key? Well, we don't know yet. But we can do any arbitrary key. Is this key padded? And is it padded using the rules of the hash? Okay. Secret key K. The authentication key K can be of any length up to B, the block length of the hash function. Applications that use keys longer. Okay, but I want something that's shorter. See section 3. Keys need to be chosen at random, blah, blah, blah. Where do they... Because, like, here they have a block of 5C repeating many times, right? Oh, read the steps below. Oh, yeah, I did think that these were, like, references, not steps. Append zeros to the end of K to create a B byte string. Perfect. XOR with this, append the stream of data text to the byte. Oh my god, I should have just fucking read that. Thank you. Apply H to the stream generated in step 3. Okay, wait, easy peasy. Sure, okay, let's do this. SHA-1 Hmac. Maybe if this is like a one shot. Data. And I guess we are returning our 5U32s, right? And in here we also have the key, right? So here we have so we were saying before, if our block length, like here they're trying to pad this out to be 512, right? But right now we do not support a 512 bit sized data stream because we're trying to pad the message, right? So we need to answer the question of if message padding is always implemented for SHA-1 or if it is only if the message is not a multiple. You know what I mean? Because otherwise these like the block size key is like kind of too long. You know what I mean? Can we, okay. Padding. Well, a summary, 1 followed by M zeros followed by 64-bit integer is appended to the end of the message to produce a thing like this. The 64-bit integer is the length of the original message. The padded message is then... So then, like, this means that, like, it's... If you have a 512-byte thing, you have 2 blocks, right? I don't see anything that kind of says you skip that ever. Yeah. I'm not really seeing that. Okay. So that means that we have to support this, unfortunately. unfortunately. So we'll go back to multi-block SHA-1 because we haven't done that yet. Okay. So I guess we were going to have a block. We're going to have a block buffer, right? Which is going to be block bytes, U8. We're going to have block is going to be an array list that we are putting this stuff into. And I think what we're going to do is we're going to start by, when we say hash this shit, we're going to go like, block, we're going to like push, I guess we're going to like append in 2 stages, right? Or I guess it's going to be like data could be arbitrarily long. So there's some while loop in here that I don't know what the condition is. Probably like remaining is data, while remaining len is greater than 0. We say like push len is going to be the stuff that we have cached. The minimum of block bytes minus this, the amount of stuff left, or data len, remaining len. Okay, that makes sense so far. Then we do append slice of remaining 0 to push len. Okay. And then we say remaining is remaining from push len onwards. But we have to do a little check here if push len is equal to remaining len. It's empty, else this. There we go. I think because you have to be careful about like indexing out of bounds there, probably. And then we do like hash block. Hash block now is done based off of our own block. We have to be a little careful here. But I think that this is just like block is self block items here. And then I think we just do like a quick assert here. Items len is equal to block bytes. Okay. Then all of this just works. And then this push message is going to be like, or pad message, I guess, is going to be like, I guess hash block has to clear the block size. Okay. And then we're very close to multi-block support here. Very close. It's just, when does this pad happen? So we have like, this is now update. And then this is final, right? Yeah. And here, we pre-compute how many bytes to push, probably. We probably push, it's probably something like, we probably just append the, like, the hex 80, right? Unconditionally. Probably. Then I guess like we have to check if this is already maxed, then we have to clear it. Then we append the 80. Or something. Then what? Then this, probably. Just in case. Then, like, while... Like, until... For... I guess, like, zero... Like, num zeros is going to be something related to the, like, block bytes minus 8, right? Yeah. So for... But, like, then we subtract off the length of this block already. That sounds right. So if we have a lot of stuff in there already, we have less zeros. Then can we do, like, self block? Can we, like, repeat? Can we add many? Add many as slice bounded. Is this what we want? I guess. I don't know. There might be a better... There might be, like, an add repeated as well, but, like, whatever. And then we can, like, memset this to 0. Like this. Then we just have to put in... like this. Like, size buff is 8U8. There we go. We're getting there. We're getting here. We put this in the size buff. We need to keep track of the message length over time. And then we write that. So say, like, block append slice bounded of size buff. Okay. That seems kind of close. I think that's right. I don't know. We'll see. Okay. We'll see if that's right. Are we guaranteed to have enough room for the size? I think so, but, like, maybe I fucked that up. I don't know. This init needs to change, I think, because we have the buffer inside now. So this is like a self-referential struct. So now we do this. We do self.star equals. We set this. Block buffer is undefined. And block is init buffer with self block buffer. All right. Let's see if that kind of does what we want. All right. Let's see if this still does what we want. 33. We've got some mistakes here. Probably this is unreachable, no field name message line. Right, so we need to track that. So we start with 0. And every time we hash block, probably, we just increase this by 512, maybe. And then on final, we just have like something like this. Something like this, where we like take the size here and then we just rip that shit. Were we adding block bytes or ×8? Let's say message len bytes, so that's clear. Okay. Okay. Unreachable code at 111. All right, so we are hash block on update at 185. Oh, right. If block items len is equal to block bytes, we run hash block. Okay, that looks wrong. That's not like a thing I've seen before. So I think we fucked up. So let's do empty string. That's correct still. Okay. We'll do with the letter A now. And that's wrong. Okay. So what the fuck are we doing wrong now? Let's see. Hash time. So we do only do one hash, which should be happening on final after we push all the padding, right? Final hash time. Yep, okay, so we're only doing hash block one time, so it must be that the block that we're pushing is not what we expect. So let's take a look. Okay. Oh, I think our hash block is the guy doing the the size appending, but it shouldn't be. It shouldn't be. That should be done maybe like here or something. I don't know. Or even maybe here, we know that we process data len. So it's just like every time we call update, we push data len, and we call final, we take what's remaining in the buffer. And that's already done. We also multiply by 8 there, right? Because this is... Yeah, that makes more sense. That makes more sense. So now we have a length of 8 bits, which I think is more correct. I see an 8 at the end there, and if we run the Python version of this thing, those are in fact the same number now. And then can we test hello again? That's working as expected as well. So now nothing's broken. Now can we try doing something that's really long, right? So can we say, give me a 64 A's, A64. Okay, we'll try this. And we're gonna hash A64 now. Okay, and we're gonna do that in the Python version as well. So how do you do is it like A64 like this? I think it is. Nope. Is it just times? Yep. Okay. Okay, so bad news. We're actually very close. Why does the... Oh, we're just not padding. Wait, this is correct. This is correct. It's just that our thing doesn't have the leading zeros because it's not doing that right. But that's good. That's good. That's good. We have multi-block hash correcting. Right, this is just supposed to say 0098BA82, but it just doesn't because there's no zero. Like, it's just not printing leading zeros. All right. We're back on Hmac. Let's fucking go, baby. Let's fucking go. Okay. Okay. So what are we doing? We're looking for something. I guess we go back to the RFC. Okay. So we're gonna say padded key is SHA-1 block bytes U8. We mem copy in. I guess we first assert that key is less than this because I don't want to deal with that shit yet. There is something to do here. We're supposed to like hash the key dummy, right? But I don't want to do that. Less than or equal to even. Padded key, we copy the shit in. Yep. Append zeros to the end. So I guess here we start with a splat 0. Easy. XOR this with the string computed in step 1 with iPad. So can we call this like maybe this is just ret. Maybe it won't be, but for now we'll call it ret. Ret XOR, was it iPad or LPAD? iPad. iPad is a splat of, what was it? 3.6. Easy. Append a stream of data text to the B byte string resulting from step 2. Apply H to the stream generated step 3. So we're doing this iteratively instead, right? So we're going SHA-1. I guess this is the return. Maybe. So this now is like this is inner, I guess we'll call it, is a good name for this. Inner. And so here we say like update with, I guess this is not just inner. This is kind of like inner start. Inner key, we'll call it. Okay, so we do this. Then we go like ret update data. Easy. And then we have this. So this is like the inner hash, I guess. Right? Then we apply H to the stream generated in step 3. Okay, so this final thing, he might want to return a 20U8. You know what I mean? And then here we kind of are going to go like for self H, we have the like word, and we have to like print out the word. So ret is a 20U8 like this, and we're going to go like ret in this index, maybe? No. We're looking at the word, maybe? Stood mem write int. Here we go. We're writing this. This is a U32. We're writing it big style into ret from I times 5 0 to 4. That makes sense. The value is the word, and we're writing it big style. So now, just to confirm, we should be able to say, like, hash is this, and we should be able to print the hash now directly, like this. And we should get, like, something very similar. He doesn't like this. Why? I times 4. So is that still correct? Yep, same answer. Cool. Cool. We're so back. So now, this thing comes out as a byte string. So, let's call this inner hash computer, maybe? This guy computes the inner hash, and this is the inner hash, right? Easy. Then we apply H to the stream generating stuff. So that's this. Then XOR the B byte string computed in step 1 with OPAD. Oh, okay. So I guess we call this K prime. And then inner key. Oh yeah, I guess we have to go like, I guess you can't XOR like this. I guess. We kind of have to go like 4 K prime byte. We like B X with iPad, right? Which is 3/6. So then we like use K prime here as inner key. And then we can kind of like go back, which is funny. To get it to like, we go like this, because it's transitive. So we can like undo, we can kind of go like iPad to OPAD is 3/6 XOR 5/6, I think. 5C. Right? And then we can kind of say like for key prime, just go like iPad to OPAD. So now K prime is OPAD or something. You know what I mean? And then we should be able to be like outer hash computer. And what are we doing for the outer hash? Append the H result from step 4 to the B byte string from step 5. So we want to use K prime and then not the data, but the inner hash. And is that the final answer? Apply H to the stream generated in step 6. Yeah, I think so. I think. That's like a maybe. I mean, we can just run it and see if it works. And if it works, we're fucking geniuses. And if it doesn't work, then we didn't expect it to. You know? Okay, so let's do a little Hmac SHA-1 of key with ASDF. Right? Easy peasy. Easy peasy. And then can we just do the same thing in test Hmac? Surely when we do the hashlib Hmac. Oh, here. Key ASDF. Okay, Python 3 test Hmac. So this is what we expect to see. Imagine. It doesn't even compile. What did I expect? What did I expect? 194, main, 194, okay. Pointer capture of non-pointer type. For K prime. Ampersand. Throw a little ampersand on there. This thing is like, I wanted 5. No, we want 20, bitch. Oh, 5 U8s. My bad. No way. Oh, first try, fucking baby. Let's fucking go, dude. Let's go. That's an Hmac, dude. Look at that shit. Oh, woo, woo. Let's fucking go. Which means that we should actually be like shockingly close to the right, like the final answer, right? Right? Because like TOTP is we do this Hmac with the key and C. We don't know what C is yet. We're the secret. K is the secret, and C is the counter value. We just have to huck a time in there, right? T is current Unix time minus T0 over X, where the default floor function is used in the computation. For example, with T0 equals 0 and time step X is 30, T equals 1 if the current Unix time step is 59 seconds, and T equals 2 if it's 60 seconds. Oh, so current Unix time is in minutes? Oh, wait, no, I see. Based off time step X. Sorry. Yes, so this is in seconds. Then X is 30, so we get 60 is 2, 59 is 1. I think that makes sense. So every 30 seconds, T increments by 1, starting with some T0. So I'm assuming that the default time step is based off of Unix epoch. And it says, I think it said the default X is 30 somewhere. Yeah, here. So they have X default value is 30, T0 is 0. So we should be able to be like, okay, so if we take this secret and we do a little, let's pull in Python 3 packages, PyOTP. Because I tested this last night, and using PyOTP to like validate this website worked. So if we just go like test OTP, import PyOTP, we say like PyOTP dot, how the fuck do you use this again? TOTP, this. Okay. What was I expecting? Oh, I have to type now. Okay. So we should be able to get something similar with the hashlib and Hmac and hashlib things, right? So we should be able to be like, hey, this is our secret. And we should be able to be like, we should be able to do this, right? So we have our key is secret. And our data is the Unix timestamp, right? The question is what format does that go in as? Right? Does it go in as a 64-bit number or a 32-bit word? Or does it go in as like a serialized sequence of bytes? None of that is clear. So let's go back to the TOTP spec. It looks like, based off this stuff, that they're using it as a 32-bit int. Specified here. sorry, this one. 4226. Is this the one? 4226. Here we go. So we just want to figure out here 8-byte counter value. This counter must be synchronized. Okay, so then how do they feed this into the SHA-SOM? Generate this. Generate a 4-byte string. I'm more confused about like the key, the counter and data values are hashed high order byte first. It sounds to me like they are doing take the 4 bytes for the counter and just kind of hash them as a sequence of bytes. That's what it sounds like to me. So how are they doing? Oh, there's more to this, by the way. There is more to this. So they're doing, they use the Hmac. They generate a 4-byte string. So DT is defined as what? Jesus Christ. Okay, I want to do, like, is there a, does PyOTP let us do not the TOTP, but HOTPs? Like, can we do that? Man, or, dir PyOTP. Let's start here for a second. So they do have HOTP. Which seems to have generate OTP. Maybe it's in the docs here. PyOTP. Do they tell us how to do here? So you have a secret and then you just call add. I see. So they're like, give me the secret. Like this. And we say like HOTP at 0. Now can we print that? Yeah, okay, cool. Cool. So now we can try to get to the same answer that I got to. HOTP, key and counter. Right, this is kind of what we're expecting to see. And we're expecting like a string of 6U8 output, maybe? I think? I'm not sure yet. Not sure yet. So which one of these like 40 RFCs was HOTP? This one. So generate an Hmac using the key and the counter. So here we're going to be like counter bytes is we're going to do like a std mem write int into from a U32 into counter bytes as big style. Okay. Then we're going to be like, give me a Hmac of that thing. Like this. Okay. Then what? Generate a 4-byte string. So we're like, DT Hmac is something. So we're like, S bits, I guess, is what it's saying. It's saying make those S bits. And then they're like, snum is st num S bits. Okay. Then what do they do? The return D is snum mod 10 to the power of digit. What? Return D equals snum mod 10 to the power of digit. So I assume this digit is probably, this is probably like not fully defined, but we're using 6 digits probably. Probably, I guess, right? System parameter, yeah. So here we're assuming 6, right? So it's just like mod a million. Sounds like it. So we're probably doing this. What does DT return? Returns a 31-bit string. So return the last 31 bits. 31? Okay. So they kind of want like a 4U8 out of this, I guess. And then they want... You're implementing HOTP in Zig? Yeah, well, we're trying... Yeah, we'll just say yeah. We are, in fact, doing that. Well, we're doing TOTP because my phone's broken and I want to know how it works. That's kind of the answer. Ooh, example. Okay. Well, let's go back here. Let's look at the DT. Let's look at DT. What is the expectation here? The low order 4 bits of string 19. What the fuck does that mean? Low order 4 bits. What does that mean? What does that mean? Offset bits be the low order 4 bits. So that's 4 bits, some nibble of string 19. Then they're calling st to num on that thing. Oh, okay, and then st to num looks like... for example... st to num, denote the function as an input string s, returns a number whose binary representation is s. For example, st to num 110 is 6. What does that mean? If s is a string, then si denotes its ith bit, not byte, bit. Okay. So this just doesn't have to exist? I think. Because our thing isn't really ever a string to begin with, right? It's already just like a sequence of bits. Okay. So st to num is kind of like garbage code. So this thing can just return a U32, and then this doesn't have to exist. So here, I think that this is just saying, like, offset is Hmac 19 truncated as U4? I think that's all this is saying, right? I think. Then they're like, P is the last 31 bits of P. String offset to string offset plus 3. But isn't that only 3 bits? According to this? But we want, like, what the fuck is going on? This doesn't make any sense, right? P is equal to the string at offset, right? Inclusive range or maybe exclusive range to offset plus 3, probably inclusive, right? So this makes it sound like this is 4 bytes, right? That's what it sounds like. Which would make sense because this would be in bytes too. Right? Okay. I guess that's fine. So we're going like Hmac from offset 0 to 4. And then this is like an int read int. Probably big style. Everything's always big. And then we truncate. Ret and then and 0x7f f or something. I think this is what they mean, but it's like really unclear to me. Like really, really, really unclear. I think that's what they mean. It's just so fucking confusing. It's said so strange. Can we ask the fucking idiot? Or is there like a C? Oh, they have an example. Maybe the example will help. Oh, yeah, right. Okay, this is way more easy. So we should have just read this. This is what I said. This is what I said. This is the same. This is the same. Pretty sure. Pretty sure. Well, let's fucking try it. Hit me with a HOTP? Why don't I even bother with that shit ass pseudocode? Yeah, I mean, the C code was way more simple. It was like way more obvious. Way more obvious. We were like key ASDF. Expected U32. Oh, right. We're doing, Am I stupid? Key and 0, right? What are we doing here? Oh, we had ASDF. No. Oh, we're using this as our secret. I guess pointer here makes sense. And can we just return a U32 here or something? Fuck it. He's like, yo. Didn't I just put an ampersand here? Hello? And then can we print it as decimal? And then what is the other example? Okay, we're not getting the same answer. We're not getting the same answer. Okay, what are we doing wrong? What are we doing wrong? So, I mean, the only two things we could be getting wrong is like there's only really two steps, right? um Okay, so they look at the last byte, 5A. Did we do that part right? Offset. Truncate the last value. Yes. The offset value is this. The value of the 4 bytes starting at byte 10 is this. So that's this here, right? Which is the dynamic binary code DBC1. The most significant bit of DBC1 is 5. So DBC2 equals DBC1 equals this. Oh, so they're like, yo, you just clear. They're talking about clearing the top bit, which is fine. I think. Yeah. Okay. Can we try this with their example number to like reduce Oh, are we? Yeah, so instead of this, can we do const Hmac is a 20 U8 is equal to this? Just to see if we're doing that part right, right? So take the pipe, replace the comma, and then everywhere here we need to do a 0x. Boom, throw some 0x's in there. Do you have the correct byte order? Maybe not. I don't know. There's a good chance that we don't. Okay. Oh wait, 872 not wait, 872921. That was the number they had, right? 872921. So this part seems correct, which means that maybe it's the counter, like it's the actual computation of this thing. So maybe this is little. Although that's wrong too. So maybe we're wrong about the conversion of the counter value to this thing. Right, so we should also double check our secret. I mean, I don't see how that... Okay, yeah. Yeah, it must be conversion of this thing. It must be. So can we double check that in the spec? Where do they do Hmac? I mean, it looks like maybe they're concatenating the two things together. Oh no, I mean, maybe not. We are running with 0, right? I mean, so here, no matter what, that thing should be 4 zeros going in, right? Like, that's kind of what this should be. Like... Right, we do see a bunch of zeros, so the byte order doesn't even really matter here. Shouldn't. Which means that this thing, but just must not be what we think. Can we look at what pi OTP does? I'm kind of down to cheat a little bit. So when they do this guy, like, what the fuck are they doing? Generate OTP. Hello? Where is that defined? Oh, because they have a super. So they have OTP. So here they have input as an int to byte string. Maybe this is the interesting part here. Turns an integer into the OAuth specified byte string, which is fed to the Hmac. So they are taking append I. Okay. Wait, isn't that fine? Isn't that what we're doing? So they're just saying, like, for each... Yeah, they're just taking the first byte that goes in is I, the lowest bits. So they're doing little endian. Oh, but then they're reversing the result at the end, which is funny. So it is big style, it looks like. Ooh, but the byte secret, they have padding. Maybe this is what we missed. Maybe this is what we missed. Oh, it's also base 32 decoded. I'm sorry. What the fuck? Did we just completely miss that? Was it base? I'm sorry. What in the fuck? How the fuck was I supposed to know that part? I lost the source code. Hold on. Where was it? That's crazy. Byte secret. Yeah. So can we actually just check that? Like, is that true? Was it base 32? Base 64, base 32, decode, secret. B32 decode. And then can we print this as a... Which they have this thing called byte array, I guess? That's unhelpful. Can I print this as numbers? Python print byte array as hex. Oh, cool. Love that. That's some cool. Cool. That's some nice Python, baby. Wait, it was like this for x in. We do have to print it, I guess. So maybe this is our key? Maybe? Maybe. We can try it. We can try it. Okay, so this is 0x, right, comma, oopsies. 0x, nope. 0x, right, comma, space, go. Let's try that. Fuck. $30.98.30. Still not right. Holy fuck. We're looking again? I guess they do have this. If missing padding. Oh, I guess, okay, let's just do their whole thing. How about that? Let's just print out byte secret. And then this guy's gonna take in secret here instead. Wait, is that what we got last time? It is. Unfortunate. That shockingly was not it. It is right. You've implemented it as OTP. Thank you. Spherophore is OTP. It's perfect. All right. Well, it's annoying that I don't really know which way we've done it wrong. Byte secret, int 2 bytes. Plot twist, Python's version is wrong. No, because I tested it yesterday. I know that it's giving me the right answer. This part is all what I expect. Did we get this wrong? What the fuck is this? 10? What the fuck are they doing here? 10 billion. Oh, this is fucking garbage int conversion bullshit. I see. Yeah, okay. So this is 0, right? Is this right from byte right bytes? Yeah, blah blah. This doesn't matter. This I don't think matters. I think either way, our 0 should be right for the input, the second half. So they're going. Digest is the thing we computed. So digest is SHA, Hmac, whatever. What we implemented. SHA-1. This is SHA-1. It looks like Big Indian, but then there's like a reverse in here. So I don't know like what the hell this is doing. It's one of the two. I'm not really sure. I agree that this looks big, but then they throw a reverse in here, so it might be little. But I mean, like, who knows? You know? Who knows? Oh yeah, there is also. There also is here. Wait, are they masking out high bits in generate OTP? No, this is all behaving the way I expect, I think. Huh. I mean, I guess we could also check this int to byte string and see what it's returning, right? I don't think there's any reason to not check this. So can we call int to byte string on 0? Yeah, that did what I expect. I think. Ooh, it's twice the length. That's twice the length. That's not what I was expecting. So it looks like a little endian U64. Not a. Okay, let's try that. Let's try that. Maya, thank you for the raid. What's up, y'all? What is up? We are implementing TOTP from scratch today because my phone. That's the fucking number, baby! That's the fucking number! The same number! That's the number! Sorry, okay. Raiders, what's up? So I ate shit on the concrete a couple weeks ago and I broke my phone. And then I bought a new phone, but then it ran out of batteries and it doesn't charge anymore, so I can't turn it on. So for the past like 2 weeks, I've just like had no cell phone. And then I'm like, I can't log into websites. Why the fuck is this shit on my phone? Why do I have like two-factor authentication on my phone? What even is two-factor authentication? What is going on? And so today we are implementing two-factor authentication client from scratch. And so we implemented SHA-1, we implemented Hmac SHA-1, and then we just finished implementing HOTP, which is a building block of TOTP, which is the thing your phone uses when you get those 6 digits. Change battery, yeah, maybe. We'll see. I don't know. Well, we've got to fix it. But the point is, I shouldn't be so tied to my phone, and I want to know what this thing is. What about this phone? We'll get there one day. One day. Okay, so we have HOTP. Anyways, thank you, Maya, for the raid. Hope you guys had fun over there. Stick around if you're interested, but obviously no pressure. Thank you for the raid. Okay, TOTP. The last step. I think TOTP is you just huck a Unix timestamp in there, right? It was like const now is we grab the Unix timestamp, which do we need maybe a IO instance for this? Maybe. So I think we have like a little IO in here, and we're looking for like a stud IO, maybe stud time. where does this like come from? How do we get like now? How do we get now? Epoch sounds like now. Maybe it's like stood time, stood IO instant. I know it's in here somewhere. Timestamp. Now, okay. With real time, right? This is number of seconds since epoch. Great. And so then we have T, which they said was the number of seconds since the Unix epoch over 30, I think. 2 seconds over 30. And then we should just be able to shove T in here, right? I think. Maybe like that. Okay, can we try confirming that we get the same thing in Python land if we go TOTP me the fuck up with now? Hit me up with what is the TOTP for this thing now? Not looking promising. Not looking promising. Okay, so what are we doing wrong? Let's look at how that Python project does the TOTP, the time part. TOTP. So they're inheriting from normal authp. Now they're calling self timecode with datetime now. And is their timecode doing some whack shit? Ooh, okay. So interval was 30. I guess we might not be UTC. Do they want UTC time? I don't know which one of this this thing were like. Okay, so if we have time zone info, they're looking to get the UTC time for that thing, right? Right, that's what they're doing. They're just going like, hit me with the UTC time for this thing, which I would assume is what we're doing if we do this. Can we print T? What is this? This. Date. Oh my god. Date this. How do you do date? How do you print the date again? Convert seconds since epoch to a date. There's also like an at thing, I think. Like, don't you just do like, I seem to remember like this being a thing. So this is can we ask for UTC time? What is like, okay, can we Unix time stamp converter? I actually don't know if this is in local time or not. GMT. Okay, so this is UTC timestamp. This is UTC timestamp because it's like in my time zone, it's right now, which is correct, and then it's like way later in the day in GMT. Okay, then what the fuck is the problem? What the fuck is the problem? Is the interval wrong? What is interval supposed to be? Interval is by default 30 seconds. Unix time is not relative to time zone. That's what I was pretty sure about, but I wanted to double check. Okay. So can I print my time code then? Okay. So we're like, bro. So my time code is this. What are they getting in Pi OTP? can we just call their function? TOTP. So we should be able to go like into their thing, and we should be able to go like print pi OTP TOTP. I guess it was like a time code for date time now, right? Is like what they were doing. Is it date time dot now or something? Yeah. So this is their time code. Oh yeah, this is their time code, this is our time code, right? So this is the same. These are the same. We've got the same frickin' number, but we're getting a different output, which is interesting. Right? Very interesting. Very interesting. So they're calling timecode with generate OTP. I'm actually so confused. Does the constructor do something crazy? SHA-1, intervals, interval? Okay. I don't see any reason why we should be getting a different answer. Considering that we got the same answer. We divide by 30. I think we have that somewhere. We have the divide by 30 here. That looked like monotonic time, not real time. I think we just confirmed that the number we printed here was the Unix timestamp. Generate? Let me just... Yeah, they're calling generate OTP with the same thing, which we confirmed we got the right answer for, right? When we said HOTP key with 0, and then in their version, we did HOTP at 0. Oopsies. We got the same number. Oh, wait, maybe we did the wrong thing. Can we do at 1? Ah, okay, we're doing something wrong here. We're doing something wrong here. It was big. I'm an idiot. This is big Indian. Yep, my bad. Big. We need to get big, not little. So big right now, not little right now. Oopies. Oopies. Let's fucking go, baby. That's a fucking OTP number. We fucking got there. Let's fucking go. Jesus fuck. Okay. So what did we learn? What the fuck is this thing? This whole day I was like, what even is a TOTP? What does it even mean? And so I guess we now know. We have all the pieces, right? So the secret code, actually just to be sure, so that we can prove to ourselves that we are correct. Let's do this authentication test. So if we run zig run, we paste this code in here. Login success, baby! Okay. So we have a secret key. The secret key they gave us was a base 32 encoded string that turned into the key that we use for HOTP. We use the time code is the Unix timestamp over 30. HOTP, Harry Potter, Harry Topper. To do a HOTP, we take the number, the timestamp, we big endian stick it in a U64 or into 8 bytes, and we do a Hmac SHA-1 before basically like, dude, this part's so weird. You like do the Hmac, and then you pull the last byte of that thing, and then use that as an index into the rest of the thing, and then you mask off the bottom 31 bits. I don't fucking know, man, for some reason. I'm sure there's a reason, but like whatever. Then for the Hmac, that is a hash of the hash concatenated with the hash a different time. What was it? It was hash of key XOR OPAD plus the hash of key XOR iPad. I think it's like something like this for some fucking reason. Because like we were trying to like prevent some sort of like injection attacks or something. And H was this shit where you have like these numbers, these 32-bit numbers that they put in the RFC. You punch in blocks of 64 bytes and then just do like this shit on them. I don't know. I don't think I really understand like the SHA-1 stuff. I mean, we got it working, but I will bet like most people don't understand the SHA-1 stuff, including people who have implemented them, right? Like SHA-1 is very much like someone at the NSA did some math, right? And they're like, can you copy paste this math into your code now, right? So we'll kind of say, okay, SHA-1 is SHA-1. We live with that. We at least can implement it like from scratch. I'm air quoting as much as like you could do from scratch, right? Because I don't know how many people in the world could make up SHA-1 from scratch. I would imagine that number is like very, very low, right? But like, given that someone gave us the math, we can implement it. The Hmac stuff was not that hard. It's just like a thing that you have to know how to do. And then on top of that, the TOTP stuff and HOTP stuff was, again, just know what to do. But once you know what to do, it's not that hard. So do we glean any like interesting information from all of this? Right? We glean the information that the codes are 30-second intervals, which you could have figured out by just looking at the app. We know that there are like just shared secrets that are base 64 encoded whatever length strings. We don't even really care what they are. We know that there are like parameters for these things that you could tune, but in reality, your like TOTP app on your phone is literally just a timestamp and a list of keys, right? That's really all it is like a list of app to like this. Okay. So I guess we learned nothing. As is the way around here. We did it, but we did not glean any useful information, but it was fun. So I think we call it there for today. I think this was a success. Guys, we did it. We wrote a TOTP app from scratch. Come on, that's fucking sick. That's fucking sick. So yeah, we'll call it there. Thanks for watching. If you like what you saw, we stream most days, maybe every other day, like 12:30 Pacific time to like 3 or 4 Pacific time. Our long-term project right now is a soft phone. We are eventually going to get back onto our Wayland client. There are some people in chat who have been waiting months for this. We will get back there eventually. But I have to fucking finish my VoIP client so I can answer my door first. So we'll probably be back on that tomorrow, the next day. I think we have to do a bunch of like UDP negotiation stuff where you like stun, turn, ice. If you've ever heard of those words, that's coming up soon. RTP, that's coming up. We've got some work to do there. Check out the Patreon, check out the YouTube, check out Twitch. You're on Twitch, Twitch Prime, etc., etc. Cool. YouTube, peace. Twitch is wanting someone to raid.